So why don't we start? And I think a couple of more people will get on as we continue. And so we're very happy and to have Wei-Kuo Chen from the University of Minnesota. So please, Wei-Kuo, you can see the title on the screen, and please, Wei-Kuo, proceed. Thank you.
Okay, thank you very much. All right, thank you everyone for coming to the talk. Yeah, I don't know the composition of the audience, all right, so maybe from different backgrounds, but in any case, if you have any questions, please stop me, all right? Feel free to ask me questions. All right, so the title is already clear that I'm gonna study, I did not say here, but the Sherrington-Kirkpatrick model is a spin glass model. All right, and I'm gonna look at a particular quantity, the so-called local magnetization, and try to understand this object in the algorithmic or maybe more numerical perspective, how to simulate some quantities like that in this kind of model. All right, so the whole talk is based on the joint work with the Si Tang at the Lehigh University. All right, so to begin with, let me just start with something very basic about spin glass models. All right, so in physics, it's really just a special some alloys, something like you see in copper and manganese, and also the iron and gold, right? This kind of alloys, and then you see that the somehow when you do the experiments, they exhibit many different behaviors compared to the usual magnet. All right. So I can just roughly speaking that, for instance, we know that the one of the important quantity in this kind of business is the so-called specific heat, right? And other one is the so-called susceptibility, all right? And those are two important quantities in studying this kind of a model, and somehow their critical temperature are different, right? In statistical physics model, usually we expect that the no matter you have maybe you might have a different quantities, right? Different related quantities, but as long as you are talking about the same model, usually the critical temperature should be always the same, but somehow in this model, this is not the case. All right, and that is just one instance. There are many things else, including aging or some different behavior of the dynamics. All right, so overall, just some strange behavior, and then the physicists just try to. We want to understand what is going on with this. All right, so mathematically, the formulation of the spin glass model is very easy to formulate. All right, and in short, what is this? This is a spin system. All right, spin system with the both ferromagnet and antiferromagnetic spin interactions. All right, so there will be two different type of the interactions competing with each other, and of course, there should be some phase transition depending on the competition. Okay, so this is a very rough picture. All right, so if you are talking about ferromagnet, like the easy model, then we know that it is going to be at the low temperature. Maybe the ground state energy, right? But at a very, very low temperature, you see that the spins are more likely to point towards the same direction, right? But for spin glass, the behavior, because of this ferromagnet and antiferromagnetic spin interactions, each location, the spin can be up or can be down, right? Or can be any other, the other possible directions. All right, so this is just the spin glass picture. All right, so the first important model is the so-called Edwards-Anderson model. All right, so this guy is, if you are familiar with the Ising model, this guy is a disordered Ising model, in other words, right? Because what I'm doing here is literally that I again, the easy model was that I look at the ZD, right, the D lattice, and then look at the small box, right? So here should be to a D power. All right. So the interaction is defined as the just from your neighbors, right? So as long as I minus J is equal to 1 in distance, and then you want to define the interaction between these two locations, I and J. And then the interaction is defined in just just two locations, I and J. All right. And now the what I mean by disorder is simply means that I'm gonna put randomness in front of the interaction for every pair. All right, and this Gij, they are IIDs, they're not normal. All right, so you see sometimes you might be up and it's down, up and down, so it's really complicated. All right, let me give you a really, a quick picture why what is so difficult in this model. All right, so again, if you are, let's say we are, just look at the two simple scenarios. All right, here is a ZD lattice, of course, but here's a triangle. But just for simplicity, the ideas is the same. You look at the triangle or the square lattice, they share pretty much the same difficulties. All right, but let me just look at this interaction here again. The interaction defined only, according to your neighbors. All right, so let's say I have three vertices, 1, 2, and 3. All right, and I know that I've been given the G12 and G13, G23, and let's say all of them are positive. Okay, so now let's say if I want to compute the ground state energy, right? It means I'm gonna look at the minimum. I'm gonna look at the minimum of these objects over all possible sigmas, right? So if I let's say I look at this spatial case and then I start from 1, right? And let's say at the location 1, I'm gonna point up, right? I decide to go up, all right? And then because G13 is positive, then I know that since G13 is positive, so I know that in order to okay, so here I should be more careful. So here I'm gonna look at the maximum of the energy, right? So if I decide to look at a maximum energy, then here is 1 and this is positive. So here, of course, I want to put 1 in order to increase the value. Okay. And then similarly, since this is positive, so I know 2 is I better to put it up, right? In order to, again, maintain that everything is positive, right? And then if you go this way, that is also fine because this is positive, then you know here is 1, right? But right now, if you have a slightly different sign among the G's, right? Say here is negative, but the other 2 are positive. Then you see you go. Let's say 1, 2, and 3. Then you see if you go 1 to 2, and since this is positive, then you know here is positive. You want to put positive, right? And then here 2, 3 is positive. So since here is 1, so you want to put positive. All right. But on the other hand, if you go along a different route, let's say 1 to 3 directly, then since this is negative, then you know you better put a negative sign for here in order to increase the value. All right. So the way that you assign the spins are really highly dependent on how these G's are given, right? Depending on the sign. Yeah, and right now, given that this lattice is a simple object, but you have many different ways to assign the Gij. So it's really a complicated problem to find out the ground state energy. All right. So usually this behavior is the so-called frustration phenomena in the spin glass. All right. So the object I'm gonna talk about is the mean field version of the EA model. All right, so the formulation is pretty much the same as before, only now I have this, I removed my geometric constraint. All right, so originally I have the Ij to be neighbors of each other, but right now Ij is any pair, right? So you can imagine that the Ij is an edge connecting the I and the J, right? So what I'm summing here essentially is an interaction defined on a complete graph. Right, defined on a complete graph. And then the G again, like before, just normal, standard normal. All right. So in this case, of course, this is a sum of normals. So the outcome will be, again, this is a Gaussian process. right? So if this is a Gaussian process, then we certainly, I mean, can compute the variance, like covariance. So it's pretty straightforward. It's given by the square of the R12, and this R12 essentially just measure the similarities between sigma 1 and sigma 2 in average. Right. This is very, I mean, this computation is very straightforward because you just rely on the IID, right? This is IID standard normal. So when you compute this and then you multiply the two pairs together, only when the two edges are identically the same, then they will survive. Right. So that's the reason why you get this. Okay. And this guy, there's a technical, I mean, there's a useful terminology for this. People usually call this as the overlap, right? Overlap. All right. I cannot touch this object too much. I mean, there are a lot to say to today, but in easy model, the important parameter is the magnetics, right? The magnetization, right? In easy model. But in contrast, to understand the spin-glass model, the important parameter is the overlap instead. Right, so there's a major difference here in easy model and then the spin-glass model. We care more about the overlap. All right. So as usual, this is a standard terminology. I'm gonna define the Gibbs measure. Okay. So for a given inverse temperature, beta, and external field, then the Gibbs measure is just defined in the usual way, right? So you have the Boltzmann weight, exponential beta h, and then the linear, just a linear interaction. All right, and then you divide it by the Zn, and Zn is just a normalizing constant. Now be the sum of the total weight, so that this guy become a probability measure. Okay, and then since you have a probability measure, you can define expectations. All right, so this notation here, when I have a sigma 1 and sigma 2, it simply means that the independent sampling from the GN, and I'm gonna compute the expectation of this f of sigma 1 and sigma 2. All right, so now here comes the important object. Okay, so as I said that in spin-glass, we care about high temperature and low, I mean, we care about the overlap. All right, so when we say high temperature here, we care about that when your overlap will be concentrated at a constant Q, right? At some constant Q. All right. So I literally just define my high temperature regime to be the collection of all beta and H. All right. Both are non-negative number. I mean, both are positive numbers, so that the overlap is concentrated at Q for some Q. All right, and this Q is not arbitrary. Indeed, it will have to be determined by some consistency equation, like here. All right, you don't need to remember this equation. That I mean, this is not that super important, but just keep it in mind that the high temperature region simply means that the overlap is concentrated. All right, and in contrast, the low temperature will be just the complement of D. Right, so pretty straightforward. All right, so now here comes a very important question. People want to understand in the past was that so how to describe the high temperature region D? Right, how to describe the high temperature region D? And this is the this is the related to the so-called the Almeida-Thouless phase transition line. All right. So the conjecture was that the D, right? The D, I mean, the formulation was super simple, just the concentration of the overlap, right? But the conjecture is that this D can be written as this set, right? So it will be all of the beta and the H that satisfy this inequality. All right, satisfies this inequality. But let me remind you that here I have a Q, right? This Q also depends on beta and H, right? If you recall from here, Q depends on beta and H as well from this equation. All right, so this is the conjectured high temperature regime. All right, and now I'm gonna all right. So in particular, there's an inequality, right? In particular, when the equality holds, right? That is the so-called the phase transition line of the Almeida and Thouless. All right. So you see this dot. I mean, this is the dot line is the is this equation 89. Okay. There have been some progress on this conjecture. All right. But overall, how to show that the 89 is exactly the boundary that distinguish between RS, between the high temperature and low temperature regime, is still open at this point. All right. So now, as I said earlier in at the title, today's title, right? Give me a second. So we care about the local mechanization of the model, right? So local mechanization is just essentially the Gibbs exploitation of each of the spins, right? So you see you have a sigma, you sample a sigma from your Gibbs measure, and then you just want to see the exploitation on each site, right? Because sigma is a vector, right? From sigma 1 to sigma n, then you just measure the exploitation on each site. Okay, and this is precisely what it is. Okay, so now this is the main question, right? So how to compute the this guy, or this vector here efficiently? All right. So if we don't know anything about the entire theory, but I just give you a measure. This is Gn, and Gn is a probability measure defined on the hypercube, right? So I have a totally 2 to the n many objects, right? So to compute this, I mean the worst case would be you need to figure out the Gn sigma for each sigma, right? And not only that, inside the Gn sigma, since this is a probability measure, so we know there's a normalizing constant z in the denominator, right? So in the denominator, we need to compute the total exponential weights, right? Out of 2 to the n many possible spin configurations. So this is a very, very huge number of the sum, right? It's nearly impossible to compute if you want to really figure out the exact value. All right, so we need to be smart. We need to think of a way to understand this quantity better. All right, so the first important sort of related result was given by the so-called Thouless-Anders-Palmer equations, TAP, right? TAP equations. So what is this? So essentially, they look at the that vector, right? The angle break is sigma, and they say, hey, this vector actually satisfies a system of consistency equations, right? So you see, if you look at the given I, say I is any number from 1 to n, then I look at this guy, angle brackets, right? And then you see the right hand side is a hyperbolic tangent, and then again this is the inner products, but here this guy is again just the object you are interested in, right? The angle break is sigma j, and similarly this angle break is sigma I, right? And then this guy here, the norm throughout the entire talk, right? Whenever I'm talking about the norms, then the norm will be the averaged L2 norm, the averaged L2 norm. All right. So if you look at this equation, yes, this is apparently a consistency equation in terms of sigma, right? This is really a consistency equation of sigma, and I mean, of course, this holds in the I mean, asymptotic sense, not exactly equal, but asymptotically, this vector satisfies this equation. All right. So this is the okay. They say that this local mechanization has to satisfy this equation. So of course, the next question is how to solve these type equations, right? If you look at here, this equation is actually quite complicated in the sense that the first term is sort of fine, right? This is the like a matrix times a vector, right? Like A times X, something like that. A matrix times A times X, and then there's another correction term. There's a so-called Onsager term. All right, this is a correction term. All right, but overall, when you look at this is a nonlinear. This is a nonlinear equation, nonlinear system of equation. All right, so how to solve this is actually very non-trivial, especially when n is getting bigger and bigger. Then how to solve this? All right, and second, even if we can find a solution of this, do we know by default that solution must be equal to the spin mechanization we want? Right. In other words, could I have many solutions? Could I have many multiple or just one? All right. So these are really natural questions we need to address, and these are really difficult problems to answer. All right. So this problem becomes sort of popular. I think it started from the maybe early, maybe in the 2010, and during that time, Boldhausen, he introduced a really beautiful iteration. I mean, motivated by this equation. Okay, so the iteration goes as follows. All right. So you see, you have this equation, right? I mean, this is sort of standard technique people will use in maybe any textbook about solving the optimizations or maybe iterative methods, etc. All right. Whenever you have this sort of consistency equations, so to produce a solution, right, to produce a fixed point, the natural way is to do like the iteration method, right? So you can say, all right, so I start from any point and I just iteratively define the next point and then put it here and then go on, so on and so forth to generate a sequence. And with the hope that in the end that sequence is convergent, then you will be that will be great. You get you get a fixed point, you get a solution of this equation. Okay. And Boldhausen's idea essentially is the same, right? Just as what I said, right? You just do iteration, but the iteration has to be sort of, you have to do it slightly, I mean, smart enough, all right? So initialization is sort of not really that important. This initialization just is not super important. You can choose anything else, that is also fine, all right? But the key component here is that usually if I were a student, I want to do the iteration, then I will say, okay, the right-hand side, I'm gonna put everything depends only on the k, right? And then I produce the k plus 1, right? So the right-hand side, I will do just k for all of them, right? K and k and k. But the nice thing about Boldhausen's iteration is that, okay, let's do the k minus 1 instead. So that means I need to, to define an iteration for the next step, I will need 2 steps in the past, right? This is the iteration. And somehow this iteration is remarkable. It really can be shown that the solution is actually convergent in the sense that first of all, I'm gonna send n to infinity, all right? And then I pass the limit for k and the k prime. So that means essentially these vectors, right, mk, they are convergent as long as n is large enough. and K, of course, super big. All right. But then you see a key ingredient is this, right? Somehow the 89 condition come into play again, right? So let me just remind you again, what is the 89 condition? So it means this guy, this inequality, right? So as long as your beta and H, they satisfy this inequality, then you will be able to show, I mean, Bordausen will be able to show that the convergence is true, right? This result is true, okay? In some sense, what that condition, that 89 condition says is that it tells you that this Bordausen's iteration is sort of, that condition is sort of some kind of sufficient condition to guarantee this is a contraction mapping, right? Something along that line. Okay, and indeed, that should be also sufficient and necessary condition to guarantee this. All right. Let's say if you look at the anywhere that say beta and H are outside of this 89 condition, right? So that means you are inside a low temperature regime. Then to produce a solution is actually still unknown. We don't even know. I mean, this iteration will be divergent. Right, this conversion, this iteration will be divergent, so we don't know a good way to produce a solution in that case. All right. So the main result I want to talk, I mean, is this. This is the maybe the only main result. They are the other two minor results. All right. So this is the if I assume that the locally uniformly, all right, my overlap is concentrated. All right, so it simply means again that my overlap is concentrated. It's just that I want to allow myself to be able to perturb the temperature locally slightly, right? So you see, I have a supremum beta prime to be between some neighborhood of beta, right? And then of course the temperature beta prime is the temperature for the system. And remember, this concentration depends on Q, and Q depends on beta prime and H, both parameters. All right, so I just want to allow myself to have this concentration uniformly locally. All right, and then we will be able to show that indeed Bordausen's iteration converges to the local magnetization. All right, this is the main result. Okay, and so now, yes, go ahead.
I have a question, Wei-Kuo. So this condition LUC, it's stronger than being in D, right?
Yes, it is stronger in D. Yes, and but actually, what people believe to be true is a lot more in D. So in D, right, as long as your beta and H are strictly inside the 89 regime, then this behavior should always be true. Yeah, so we are not like imposing this condition out of nowhere. This is sort of expected. It's just that at this point, we still don't know how to prove this everywhere in the 89 regime. But so far, we do know that a fairly large portion of the regime, essentially almost everywhere, it's just that the sort of city, there's a tiny little corner, we don't know how to handle it. Otherwise, we know pretty well that 89 essentially almost sharp, but there's a small region, we don't know how to handle it. Yeah, and so far we know that again, everywhere inside our region except that small corner, then this kind of behavior is already true.
I see. Okay, thank you.
Yeah, no problem. Okay, so now let me just comment quickly that how come this will be easier to simulate this guy. All right, so if you go back, as I said earlier, that this is local magnetization, right? So the worst case scenario, if you want to compute it, this is very time consuming and difficult. All right, but here this MK is just an iterative algorithm, right? So if you have there are many different algorithms in the world, but iterative algorithm is usually one of the is usually the one considered to be a sort of very, very nice to implement, and then the computational time is usually only of polynomial order. In this case, I think just n, the computational time should be proportional to n or n squared. That will be enough. Yeah, so you see that we tend this computational time, like 2 to the n, roughly like exponential time, to be a polynomial time. So this is the major I mean, the main consequence out of this. Okay. So let me give you for the rest of the talk. I'm gonna essentially do the proof, but not exactly the proof. But I want to tell you some algorithms that really motivated from the study of spin glasses. All right. So we have seen that the Boltzmann, he used the tab equation, right, to define this iteration, and then to show the convergence of MK, and then we get this. All right. But if I want to show this result, I cannot measure these two objects directly. Right. I cannot measure this difference directly. The approach is that I'm gonna introduce an iteration in the middle. All right. I'm gonna call that as the so-called cavity equation. Right, based on the cavity equation, and this iteration, somehow cavity iteration is asymptotically very close to Boltzmann's iteration. Right, this is the entire paper. The main difficulty is to show that these two are close to each other. Okay, and then the simple one would be to show that under this condition, technical condition, then this local magnetization is close to VK. All right, so this is the easier step, and this is the difficult one. All right, and for the rest of the talk, I'm gonna try to motivate what are the algorithms, right, about the V, and also what are the cavity equations. Okay, so the cavity equation is this, all right? So I mean, this condition, don't worry about that. What it says is that okay, so this is the local magnetization of that I spot, right? And remember, this angle bracket, the size of the system is n. Okay, and my right hand side here, this is not the same as the tab equations. This is something else, because my here this is n-1. So you see the size of the system of here is 1 less than the left hand side. This is my notation. All right. So this n-1 simply means that this is a system of size n-1. All right, and with a slightly small perturbed temperature beta prime, but this beta prime is not too far away from beta. Okay, this is the cavity equations. All right. So what it says is, if I want to understand what is going on with my system of size n, then I can actually reduce this n system problem to an n-1 system problem instead. Right, because this is exactly the equation that bridge between the n-1 and the n systems. Does it make sense? Okay. So this is the so-called cavity equations. And now let me give you a rough idea how this is proven. This is actually quite cute. All right. So to do this, let me just look at the n spin, right? There's no difference between the others, but just look at the n for simplicity. So recall this is my definition, right? This is the definition to compute this. And I'm gonna introduce this beta prime, right? This is again the shifted temperature. And sigma is just, I mean, I'm gonna look at the sigma to be two cases, 1 and -1 at the last coordinates, and see what is going on. All right. So if I look at the my original Hamiltonian Hn, right? So I put it here. And now what I'm gonna do is that remember Hn is defined, in terms of upper triangle, right? I less than j, and ij are between 1 and n. Okay, so what I'm doing here is that I'm gonna cut my triangle into the triangle from the triangle formed by n minus 1 times n minus 1, right? And I still have the last column left. All right, so this guy essentially is the last column. Right? So originally I should have sigma j and sigma n, right? This is the last column, and that sigma n is given by, since I choose here to be 1 or minus 1, so that sigma n will be here. Okay, and then this is the triangle that I cut, right? This is the triangle from n minus 1 to n minus 1, right? So this is essentially, if you put these two together, this is the same as the original Hamiltonian, right? Except that the temperature is slightly perturbed, right? It's slightly perturbed, and then the size of the system is n minus 1. Right? So just purely algebraic, nothing really change. Nothing deep at all. All right. So, but if I take this equation, all right, and then plug this guy into my formula here, right? Maybe say here, I plug this equation into here, then you can rewrite your original spin magnetization in this way, right? So here I introduce another Gibbs expectation, right? There's a prime to indicate this is the expectation with respect to these Boltzmann weights, right? So this is a new Hamiltonian, but you know that this is smaller size and slightly change the temperature, right? So you can rewrite the, you can rewrite the numerator, and the numerator is the hyperbolic sine, and then the denominator is the hyperbolic cosine, right? So you will get this equation. All right. So now I'm gonna further rewrite this equation again, just purely algebraic. All right. So I'm gonna center my sigma j, right? Sigma j. I'm gonna center it by deleting this Gibbs expectation and then add it back behind. Okay. So one good thing, one of the good reason of doing this is so right now you have two Gaussian fields, right? Left and right, right? And somehow when you do this, these two Gaussian fields will be independent of each other. This is hard to see from here, but when you compute the covariance of these two, right? When you compute the covariance of these two, then what you see is that in the end, you become just the overlap and minus the overlap. And we know the overlap is concentrated around a constant Q, so we know the correlation is equal to 0. All right. So then what you have here is that literally these two are independent Gaussian fields, and then you also have some, again, for similar reasons, this guy is actually a Gaussian random variable with some fixed variance given by this. Okay. So this is some law of large, the central limiting theorem going on here, again, because of the independence of these two, and also G and Z are independent of the angle bracket prime. So you can do this. All right. So once I get this, then I can compute the expectation in Z. So the outcome is exactly what we want. Okay. So this is the so-called cavity equation. Again, just to remind you that this is a system of size n, and this is a system of size n minus 1, right? So these two systems are they are connected by these hyperbolic tangent objects. All right. So now, what is the iteration we are going to use? So I'm gonna look at this equation and then introduce the iteration as sort of just keep iterating this equation as many times as we want, right? So this is the first, this is one iteration, right? So here, this is one iteration. So again, the left-hand side is a system of size n. The right-hand side is a system of size n minus 1. And in particular, I delete the i's site. I delete the i's site, right? Because just like a previous page here, this is n, and I delete n, right? So the sum is only from 1 to n minus 1 for the same reason. So here, I have I, so I'm gonna delete I. I delete I here and here. All right. So if you have this, and then of course I can do it one more time, right? So I can just take this and then rewrite this guy as this. I mean, as this blue and red stuff, and delete. Right now, I have to delete I and the J. Well, I and the J, and so on and so forth. So I keep on doing it, right? So you see the pattern is that here J is not equal to Y and K not equal to IJ, and L is not equal to IJK, right? So you see, it means if you are getting deeper and deeper inside your iteration, then you see that what you are adding inside along your path is a random, is like a self-avoiding walk, right? Self-avoiding walk, because all of the path, right, going from I to J, J to K, K to L, they cannot self-touch itself, right? So it's just a self-avoiding iteration. All right. So this is my cavity equation, and I'm just gonna just take this equation to define my iteration. Okay. So the iteration is this just the I mean just this is my initialization, all right, and f is just some sequence of Lipschitz functions. All right, and the iteration is sort of the same as before. So I initialize my vector, right? Initialize my vector, right? And this vs is a vector and depends on s, right? So when I put the s there, it means I'm gonna kick out those sides from s, right? So you see here inside my definition, I only define this vector for all i's inside 1 to n and delete the indices inside S. All right. So this is my initialization, and iteration just goes as before. We just again each iteration I'm gonna kick out one element, right? So this is the new vector I'm gonna define. So this new vector is defined in the same way as before. So I have a S, and I'm gonna kick out the I on top of S, right? So the sum is over OJ, not inside S union I, right? Just like the cavity equation you saw earlier. Okay. So the outcome, in the end, output is what? The output is just V. I'm gonna just look at the V and then the empty set, right? So that means I'm gonna look at the V, and then I don't want to kick out anything, and then define this iteration. This is the output we want. All right. So now let me recall that this is Baldhausen's iteration, right? Baldhausen's iteration, and then we also have the this Baldhausen's iteration is, you certainly will be curious that why is this really important to put hyperbolic tangent, right? Why it is important to consider only the hyperbolic tangent, right? So as a matter of fact, you can actually generalize this iteration in a more general scenario. And in that case, the iteration is similar to here. So you start from some initial, right? But the initial has to be done in 2 steps, U0 and U1. All right. And then you define this iteration by just by this. All right, by this. In comparison, you say, all right, the first thing is the same as here, right? The first thing is the same as here. And then here, this is slightly non-trivial, right? The mk minus 1 is also here. This is fine. All right. But then you say, okay, so this guy, how come this is equal to this? Right? This is really use the, we really use the some important property about hyperbolic tangent. All right. So in fact, that if you select the initialization and then the function f0 and f1 fk properly, then you will see that okay, so Bordausen's iteration can be recovered explicitly. All right. So this is the so-called approximate message passing algorithm. I cannot say anything too much. I mean, I cannot say more about this, but let me just comment quickly that this is one of the very beautiful algorithms that have been popularly used in many high-dimensional statistical problems and spin glass related objects. Yeah, so there are many applications out of this. Okay, but for today's purpose, what we can show is that, remember, we have the cavity iteration, right? We have a cavity iteration, so each time we just kick out one guy out. All right, and then we also have the AMP here. So now how they are related to each other. Okay, and this is the other main result. So we show that the V is the same as U, right? So AMP is the same as our cavity iteration, right? So it's sort of, this is not that straightforward to see, but here somehow each time you sort of kick out some component out of the first one, right? And the one you kick out, I mean, this guy essentially comes from the Taylor expansion of this FK. You do the Taylor expansion of the FK, then this guy, I mean, do the Taylor expansion of the FK, and then this is essentially the first order term that you will see out of your expansion. So you kick out that guy, right? You kick out the first order, the first order term, and then the zero order term will give you the cavity iteration we want. This is not so easy to see from here, but this is the quick reason behind. Okay, and then the another thing is the we can also show that the our iteration is convergent, right? Our iteration is convergent. So what you see is that again you write down your factor, right? And now you look at the it's sort of low large number stuff, all right? So then you send n to infinity, then this guy will converge to some a sequence of random variable v0 and vk, and these are jointly centered Gaussian. Jointly centered Gaussian, and then their covariance is given by, there is a regular pattern. It's actually quite cute, right? The covariance is sort of simple. You can really define your correlation iteratively from the very upper left corner, and then go up and until you match the whole entire matrix, right, by this equation. Okay, so in fact, that this equation, I mean, this result was also proved before, right? This was actually proved before earlier by much earlier by many papers, right? I mean, including Bordausen's and then the Baiati, Montanari, etc. They produced, I think, tons of papers out of, I mean, because of, I mean, to show this kind of convergence. All right, and then one of the technique they used was based on the Bordausen's conditional argument, right? So you literally really have to do the let me go back to here. So you really have to sort of conditionally partition your G properly, and then the conditionally under each MK. So you have to do the conditioning along the entire path MK. So it's actually a very complicated, it's a very beautiful decomposition, but on the other hand, it's actually quite difficult. All right, but one of the nice advantage of having, I mean, of having this VK, is that you can show this convergence would really, I mean, without too much effort. All right, so let me just I think I still have a one. How long can I go? I'm almost done.
Yeah, no. I think you have. You can take 5 more minutes if you like.
Okay, great. Let me just do this proof, then we will done. Yeah. Okay. So as I said that here you have a VK, right? And how to show this is true. Let me give you a special example to tell you why this is easy to see in the VK. All right. So let's take to V for example. All right. So remember again that these iterations are defined by kicking out more entries when you are getting deeper, right? So for instance, V1 is just the linear product here, and then you kick out the I. And then VI2 is that again, when you get in there, you kick out one more. So you kick out J as well. Okay. So this is really a copy paste of the definition. And now, okay, so now let's try to compute the covariance. Covariance. And now the covariance here is given by this is by symmetry, you know they are the same, right? They are all the same, so you just put 1 for the I. Okay. And now I just plug these two equations over here. All right. And when you plug these two equations to here, now you see that the beautiful, the nice observation is that you see when you do this iteration, right? This is 2-layer iteration, right? You have to go 2 steps. But here, the Gij, the disorder here is independent of the disorder that you see in here. This is very important because of the self-avoiding property. You see that no matter how many layers you get in there, the disorder in the future step is going to be independent of the outside disorder, right? So these two Gaussian random variables, they are independent of each other. Okay, so when we want to compute the correlation of these two, then you know because of independence of these two, then I can compute the covariance between this Gij for the top and the bottom, right? So that's the reason why in the end you see that the Gik will disappear and then simply just the products of these two. Okay. And now the next step will be, again, you use the similarity, right? Because this is the same for every J, so why not just choose J to be 2, right? So, and if you choose 2, since you have n-1 many guys, so you put n-1 over here, all right? And also, I'm gonna use the independence of the Gij and then the Gjk again, so that I can write it as individual expectations. All right, and now we almost there, because right now this guy, this guy is essentially the expectation of F0 V0, right? Be careful. This is just the second index of the initialization V. So we know this guy converges to V0 already. And then this guy here, G2K. You want to compute this, right? You can write these complicate objects, right? Complicate sum here as a normal random variable, right? And just put down some appropriate mean, right? Appropriate variance. The variance here, when you compute it, it will be the sum, right? It will be 1 over n and sum over k not equal to 1, 2, and F0 VK square. And then, right, that is your variance. But because of law of large number, I know that 1 over n and sum F0 VK square will be convergent to this guy. All right. So you see that in the end, just according to, if I define this as my V1, then that is the V1 you see from the statement of the main results. All right. So really, because of the this cavity iteration, sort of you define the iteration by the self-avoiding path. So somehow you have a more independence when you want to consider the interaction of the two different indices, VK and VK plus 1, something like that. Okay, so I think this is the end of my talk, and I want to thank you guys.
Thanks, Wei-Kuo, for a very nice talk. Could I open it up for questions? If anybody has a question.
Yeah, I just wonder. So okay, you started from a Gaussian iteration, so maybe you could take something else like a Bernoulli between spins, and I would like to to know how much does it go through if you change so Gaussian to say Bernoulli or some other distribution.
Yeah. So yeah, there are many universality in this model indeed. Yeah, so the yes, if you want to derive the cavity equation, right? Cavity equation like the one we saw over here. Right, cavity equation. Yeah, I think that would be still fine. I mean, you see the again, the thing is the thing is that you just do everything, right? I mean, the thing I'm doing here is quite formal. You just get up to here, right? And then you know, yeah, probably this is the key in the yes. Yeah, because right now these are not independent. I mean, you cannot just use the look at the correlation to determine if they are independent or not. Yes, so there might be some subtlety over here. Yes, that's a good question. I did not think about that. But on the other hand, I mean, also common in case you are interested. Actually, the for the this AMP, right? The AMP, this is actually universal if you define different G's, right? If you look at a different disorder matrix instead of Gaussian, then the outcome of this AMP you will still get the same convergence. The convergence will still be the same. It wouldn't change at all. Yeah.
All right, thanks.
Sure.
So maybe I could ask a question. So the local magnetization is like the mean. How about other moments? Is that something of interest or?
Yes. Yeah. Yes. We can certainly. I would say that the most interesting case should be the local. I mean, there are many different objects, but including the one that I said earlier, overlap, right? Remember the overlap was defined. Let me go back here quickly.
Sigma I times sigma j.
Yeah. You can say, all right, so we can, how about computing this? Yes, that is another interesting object. But you see, if you want to compute this guy, right, compute this, and the expectation of this is just the sum, I mean, 1 over n, and then the sum of the angle bracket sigma I1. And I mean, maybe I should go to the, maybe here, almost there. Oops. Yeah, here, right? So here I have a sigma, I have a sum, right? So if I want to compute a Gibbs average of this, yeah. And now somehow this quantity is if you look at the Gibbs expectation, since 1 and 2, they are independent sample from the same Gibbs measure, right? So then what you see is indeed just the second moment of the, I mean, not the second moment, I should say the square of the local magnetization. Yeah. And so essentially I mean, this is the most important quantity and can be related to, I mean, can be simplified as the local magnetization. Yeah, there might be some other, I mean, for the SK, right? For the SK, the most important quantity is the overlap. Yeah, but if you are talking about other models where you impose some, I mean, where maybe the interaction is not as good as complete graph, right? You might have something like a Eric-Rennie graph. Then that would be the so-called diluted spin glass model. All right. In that case, the important parameter is no longer the overlap. I mean, it's actually much more. In that case, the entire system will be dependent on the so-called multi-overlaps. Yeah. So this is just the two overlaps, but you can define three overlaps. That'll be sigma I1, sigma I2, and sigma I3, etc. So you really need to have all of the overlaps in order to determine the behavior of the system. Yeah, but overall, those quantities can be boiled down to the computation of the local magnetization, more or less.
I see. What you mentioned that in low temperature you don't expect this kind of convergence.
Yeah. The low temperature, right? The low temperature again inside this region, the outside of the D. So in this case, there are many. In low temperature, right? This equation should have exponentially many solutions.
So it's non-uniqueness or something like this.
Yes, essentially not uniqueness, right? Exponentially many solutions. But what I'm asking here is just something even more basic. Can we simply just produce a solution? There should be some ways to show they are exponentially many, right? But what I'm asking here is that can we possibly find an efficient algorithm to produce just a solution? All right, this problem is actually still not quite well known. I mean, still open.
So your fixed point method, doesn't it give uniqueness in some sense, or?
No, you really need the Bordausen's. I mean, you need the 89 condition. You need this condition to guarantee the convergence of this. All right. Essentially, it's just like the one way to if you have a real value function and is a self map, and then you want to determine if that guy has a unique fixed point, you have to compute the derivative and to guarantee to make sure that the derivative is less than 1 or less than or equal to 1. But somehow when you are outside of the 89, the derivative will be looks like the derivative is bigger than 1, so you sort of going towards the opposite direction you want. Yeah, so this condition is sort of very important, and in low temperature regime this will be violated. So we don't know. Yeah, we don't know. I mean, certainly you need to have a better iteration or something else. Just looking at this wouldn't work. Yeah, I can maybe comment a bit more. Indeed, in the low temperature region, you can even show that the distance here is given by it can be quantified, right? And that function is going to be strictly bigger than 0. So you can really quantify the distance of this two when you are outside of the 89 condition.
I see. Thank you. Are there any other questions from anyone? Okay, well, if not, then why don't we thank Wei-Kuo again? And
thank you, guys.
Thanks for coming on.
Sure,
Nice
sure.